Hello students, we are going to learn about electronic displacements in a covalent bond. You know that covalent bond is formed by the sharing of electrons. A single covalent bond means a pair of electrons. Electronic displacement in covalent bonds may occur either due to the presence of some atom or groups in the molecule or under the influence of an attacking reagent. First, we'll see what is meant by inductive effect. When an electronegative atom like halogen or groups such as NO2 group, COOH group, etc., is attached to the end of a carbon chain, the sigma electrons of the CX bond are attracted by or displaced towards the more electronegative atom. Suppose we have the carbon chain with 1, 2, 3, 4 carbons and a halogen is attached here. Evidently, the halogen is more electronegative than carbon. So, the shared pair of electrons in CX bond will be shifted more towards the halogen, making it slightly negative. As a result, the carbon which is attached to the halogen in turn develops a positive charge. Due to this positive charge on the carbon, the electrons that are shared between the neighboring carbon get shifted more towards it. So you find that the halogen will pull the electron towards it with greater force, whereas the second carbon will pull the electron with less strength, making it slightly positive. In turn, this carbon is also having a positive charge which will provoke that carbon to pull the electrons in between the other two carbons, making it still lesser positive. So you find that with distance, the inductive effect dies out. This type of displacement of sigma electrons along a saturated carbon chain is called the inductive effect or I effect. We have two types of inductive effect. Plus-I effect is known as the electron donating effect, whereas minus-I effect is known as electron withdrawing effect. So, inductive effect can be either electron donating or electron withdrawing. You find that groups which are like NO2, CN, then COOH, fluoride, chloride, bromide, iodide, or hydrogen. Nitro group is having the maximum electron withdrawing effect compared to cyanide or carboxylic acid or halogens or hydrogen. If the substituent attached to the end of the carbon chain is electron donating, the effect is known as plus-I effect. Plus-I effect is shown by alkyl groups, and you find that it will be in the order tertiary butyl group is having maximum donating effect compared to isopropyl group compared to ethyl group compared to methyl group, compared to deuterium, and finally hydrogen. So, you can conclude that inductive effect is a permanent effect operating in ground state of an organic compound or organic molecule. Inductive effect is responsible for high melting point, boiling point, and permanent dipole moment of polar compounds. Electromagnetic effect involves complete transfer of electrons of a multiple bond to one of the bonded atoms in the presence of an attacking reagent. Take the example of carbonyl group. We have the carbonyl group with the formula C double bond O. We have a pi electron here in the double bond, and in the presence of an attacking reagent, you find the pi electrons get shifted towards the more electronegative atom, making it charged with carbon with a positive charge and oxygen with a negative charge. As long as the attacking reagent is present, the charge separation continues. The moment you remove the attacking reagent, it reverts back to C double bond O. So, electromagnetic effect is a temporary effect and takes place only in the presence of a reagent. As soon as the reagent is removed, the molecule reverts back to its original form. Plus E effect is shown when C double bond C, when it combines with H positive, that is an electrophile, you find that it gets pi electrons get attracted towards the H plus ions, making it C single bond C H, and this becomes positively charged. But in the case of C double bond O, when it combines with a Cn minus group, here it is a nucleophile. What happens here? You find that Cn minus attacks the relatively positively charged part of the CO, and the pi electrons get shifted to making it Cn bonded to carbon 2 and O with negative charge. Likewise, you find that unsaturated system shows plus E effect with electrophiles and negative E effect with nucleophiles. The next type of electronic displacement occurs in what is called resonance or mesomerism. What do you understand by resonance? Whenever a single Lewis structure cannot explain a molecule accurately, a number of structures with similar energy, position of nuclei, bonding and non-bonding pairs of electrons are taken as the canonical structures. This happens whenever we have alternate double bonds in the molecule. Positive charge is separated from a double bond using a single bond, or a lone pair is separated from a double bond using a single bond, or a negative charge is separated from a double bond using a single bond. So then you find that there is a flipping of charges from the region of higher concentration to a region of lower concentration. The process is known as resonance. Consider the example of CH2 double bond CH single bond CH, double bond CH2. If you examine the structure, you find that the double bonds are alternate here. So then you find that electron starts moving from one end to the other. So you find that if these electrons are shifted to this carbon, the carbon here becomes positively charged. Positive single bond double bond. So this becomes positive and it has a tendency to attract the pi electrons towards it. As a result, this will be shifted this side, and so the final structure we get is CH2 single bond CH, double bond CH, single bond CH2 negative, whereas this becomes positively charged. So these two are the canonical forms or the resonating structures of 1,3-butadiene. Now take the case of a ring of benzene. Suppose we draw the benzene structure with double bond, single bond, double bond, double bond. Now you find that when electrons starts moving here, so suppose the pi electrons are shifted this side, this becomes positively charged. At the same time, the positive single bond double bond is there. So these pi electrons get shifted here, which will reduce the charge density on this carbon. As a result, the pi electrons get shifted this side. So then we get the second structure, which is also known as the Kekulé structure of benzene. And here you find that earlier case, this was a single bonded carbon-carbon bond, so it becomes double bond. The pi electrons get shifted in turn, so you find it, and this becomes a double bond. So you find that the actual structure of benzene is the resonating structure of these two canonical forms, and this is written as benzene ring, where the pi electrons are delocalized. So, resonance effect or mesomeric effect refers to polarity produced in a molecule as a result of interaction between the two pi bonds or a sigma bond and a lone pair of electrons. Take the case of but2ene 1-al. Here you find that two double bonds are there, one between C double bond O and the other between these two carbons. Here you find that oxygen is more electronegative, so it becomes shifted. So oxygen will pull the electrons more towards it, and with the result the pi electrons get shifted here, which in turn makes this carbon positive single bond double bond, so the pi electrons get shifted here. So the canonical form can be drawn like CH3 single bond CH, single bond CH, double bond CH, single bond O negative. So this becomes positively charged. So these are the canonical forms or mesomeric forms of. Suppose we draw the structure of bromobenzene. This is benzene ring with bromine attached here. We have three pairs of electrons on bromine. So you find that the pi electrons or the lone pair is in conjugation with the double bonds. So what do you mean by conjugation? That means it is having alternate structures in the double bonds, or you find that lone pair is separated from the double bond by a single bond. Then we say that it is in conjugation. So whenever the molecule has conjugation in the structure, you find that flow of electrons happens from the region of higher concentration to the region of lower concentration. So you find that the electron starts moving into the ring, making it more rich in electrons. So this becomes double bond. These electrons get shifted here at the ortho position, leading to the structure here. Bromine becomes positively charged, double bond will be shifted here. Now we have the lone pair concentrated on the ortho position, lone pair single bond double bond, the pi electrons again shift, it will move into the ring. This becomes concentrated at the para position, leading to the second structure, leading to the second canonical form. Here too you find that there is the separation of negative charge with a double bond by a single bond. So lone pair, single bond, double bond, pi electrons get shifted. Electrons get shifted from the negative carbon to the double bond and it gets concentrated at the other ortho position, leading to the next canonical structure. The shifting of the electrons lead to the third canonical form. Here too you find that the electrons are concentrated on the other ortho position. Here too you find that lone pair, single bond, double bond. So there is the drifting of electrons into the ring, leading to the next canonical form. Pi electrons get shifted here. These electrons come back to the original position, leading to the next structure. So the fourth structure is obtained, which is similar to that of the first structure. So we have bromobenzene with total of 5 different structures, and the actual structure has a resonance hybrid of all these structures. Hope you have understood what is resonance now. The next mode of electronic displacement that occur in the molecules is known as hyperconjugation. Hyperconjugation refers to delocalization of sigma and pi bonds, or delocalization involving sigma bond orbitals. Here you find that the scientists named Baker and Nathan suggested that the alkyl groups with at least one hydrogen on the alpha carbon attached to an unsaturated carbon atom are able to release electrons. Take the example of propene. Propene can be written as CH3 single bond CH double bond CH2. Here you find that the double bond is separated from the CH sigma bonds through a single bond. Then we find that there is a slight transfer of electrons happening here. The bi electrons get shifted to this carbon, which makes the CH bond shift towards this side. So then you find that it forms the hyperconjugative structure CHH, H positive, double bond CH, single bond CH2 negative. The next structure will be Instead of releasing this CH bond, we can remove the H plus from this CH sigma bond. So that will result to the next structure CH, H, H positive, double bond CH, single bond CH2 negative, which can again be written as CH, H, H positive, double bond CH, single bond CH2 negative. So with the result, we have 3 CH sigma bonds here at the alpha carbon, and so it forms 3 hyperconjugative structures. The alpha carbon is the one that is attached to the CH double bond CH2. Related to that, this becomes the alpha carbon. So the CH bonds that are present on the alpha carbons decide the number of hyperconjugative structures. In all these hyperconjugative structures, there is no definite bond between one of the carbon atoms and the hydrogen alpha position, and hence this hyperconjugation is also known as no bond resonance. Consider the examples of CH3 thrice C positive, CH3 twice CH positive, and CH3 CH2 positive. We'll check how many hyperconjugative structures are possible on these carbocations. First case, if you spread it out and write, we have the structures like CH3, CH3 and CH3. On counting the number of CH sigma bonds on the alpha carbons, we have total of 9 different equivalent CH sigma bonds here. So 9 hyperconjugative structures are possible for first carbocation. Coming to the second one, we have the second one with the structure CH3, this side CH3, and the next is CH with a positive charge. So the carbon next to the C positive carbon is known as the alpha carbon. This is also alpha carbon. So total of 6 CH bonds are there. So then it can form 6 hyperconjugative structures. Take the case with ethylium cation. So we have CH2 positive and we have CH3. So only one alpha carbon on which we have 3 CH sigma bonds. So 3 hyperconjugative structures are possible. So you find that the tertiary carbonium ion is always having maximum stability due to the formation of maximum number of hyperconjugative structures compared to a secondary carbocation and a primary carbocation. In this video, we have explained the electronic displacements happening in a covalent bond.